So now that you've had the opportunity to do the exploration about gases, let's go through the ideas that you've learned. One thing I want you to realize is that even though we've introduced you to various names of laws of gases, you do not need to know the names of the laws. A lot of times they're helpful for students to help them remember what the laws are, but I'm never going to ask you what Boyle's law is. I do want you to be able to tell me if these are the two variables that are changing, this is how they're going to interact with each other. But you don't have to be able to state the law. Before we go through this first analysis, I want to bring a couple of ideas to your attention, and those are a few things that you can use to help you decide what variables are changing. First idea is normally Mother Nature prefers to keep pressure constant. So she will change other variables before she changes pressure, if at all possible. If not, pressure will oftentimes move from an area of high to low because it's trying to equilibrate. Just like water runs from a high level to a low level, pressure moves from high to low as well. So if you have a container in which the pressure is changing, that's going to impact whether or not it will explode or implode, sometimes based upon what the atmospheric pressure is. So keep that in mind. That's going to help us explain one of the ideas. And then the other idea is oftentimes it is helpful to think about what kind of container you have. If you have a container that's rigid, volume's not going to change, which means probably pressure will be impacted. However, if you have a container that's flexible, the volume is easily going to change. That's probably a good indicator that pressure is going to try and remain constant because volume is what's going to change then. So keep that in mind, that the type of container will impact how volume changes, which means it will also impact how pressure changes. So those are just three ideas that I want you to keep in mind as we go through the various explanations for the 6 activities that you did. So now let's turn to the table and let's take a look at what you guys found out. So the first station, Boyle's Law, that was the one with the bubble wrap. And so what did you do there? You took the bubble and you squished it, and as a result it popped. So hopefully you figured out that volume was definitely changing, and as a result of volume changing, pressure was also changing. We didn't change temp, we didn't change the number of moles, those were our constants. So think about it, as I squished the bubble, the volume got smaller. As the volume gets smaller, what happens? Molecules move closer together. As the molecules move closer together, they're obviously going to collide more often, so what happens? More collisions means more pressure. So as volume got smaller, pressure got bigger, so there is an inverse relationship between volume and pressure. So that was the bubble wrap. Gay-Lussac's law was the one where you had the can implode on itself. So think about the container. A can is reasonably rigid, so volume is going to be constant in that case. I know some of you wanted the volume to change because the can imploded, but the can imploded as a result of the pressure change. We also had the number of moles constant because we sealed the container when we turned it upside down in the cold water. As a result, temperature, hopefully the obvious variable that was changing, and also pressure was the other variable was changing. So think about, once again, what did we do? We took the can and went from a high temperature to a low temperature, so temperature went down. As temperature goes down, what happens inside the can? The molecules move more slowly, and so because they're moving more slowly, they're going to collide less often, and as a result, pressure goes down. Now, here's where the equilibrating pressure comes in. The pressure inside the can is lower than the outside atmospheric pressure. So what happens? The atmosphere tries to push its way into the can, and as a result, the can, which is rigid but not strongly rigid, winds up imploding. So the implosion is a result of the pressure trying to equilibrate, but what we did is we changed the pressure first. So temperature went down, pressure went down. That's a direct relationship. Next idea we did was Charles' Law. We put the balloon on the Erlenmeyer flask that was on top of the hot plate and watch what happened. Well, since it was on the Erlenmeyer flask, obviously, temperature went up. The balloon is flexible, so the balloon's volume is going to change. There's our other variable. And so since the volume is changing, pressure is going to be constant, and of course the amount of gas molecules in the balloon is constant. So, was that a direct or inverse relationship? As temperature went up, the balloon got bigger, so that's volume going up. So there we have another direct relationship. All right, the next one, one of Avogadro's laws was doing the computer simulation. So this one was you were keeping moles constant, or you were changing moles and pressure. And so kind of a no-brainer there because the computer program told you what to do, which means we're keeping temperature and volume constant. All right, so once again, think about what's happening. If we add more moles to the container, what's going to happen to pressure? More moles in the same volume means that they're going to collide more often. So as moles go up, pressure's going up. So there's another direct relationship. Next one was you blowing up the balloon. So obviously that was volume because you made the balloon get bigger. What did you do to make the balloon get bigger? You blew into it. What were you actually putting into it? You were putting air into it. Molecules of air, a lot of CO2, a lot of nitrogen, and so forth. So temperature and pressure are our constants. Direct or inverse relationship. More moles inside the container. Container is flexible, so the volume is going to expand in order to keep pressure constant. So we want the same number of collisions with more moles. You've got to give the container more space. So there's another direct relationship. So we've got 4 direct relationships so far. We've got 1 inverse relationship. Let's take a look at the last idea. That one doesn't have a name for a law, unfortunately. So we just call it the no-name law. So which set of variables have we not looked at yet? Temperature and moles, but again, that was easy because that was the other computer simulation, so that lets you see what was happening. Pressure, volume, constant. So we're not changing the space. We don't want any more molecules to collide, so that's key. If we want to keep pressure constant, what do we have to do to maintain that constant number of collisions? So I add more moles in the same volume, naturally pressure is going to go up. But we don't want pressure to go up. So if I put more moles in the same amount of space, what has to happen to their motion? You got to slow them down because you want them to collide less often. So number of moles goes up, temperature has to go down in order to maintain pressure and volume. So that is a second inverse relationship. So one of the big ideas that you want to keep in mind here is that if pressure has to stay constant, you've got to think, what do I have to do to not change collisions? That's often something very useful to help you explain the reasoning. So now you've got analysis question number 2. There are 6 scenarios that I'm asking you to address when it comes to gas laws once again. So you've seen 6 back in the lab. Here are 6 more real-life scenarios. Each one is one of the 6 gas laws. So the aerosol can, which one is it? This is only going to be used, each gas law is only going to be used once. So try and figure out what's going on. With your explanation, again, use the ideas that pressure is collisions, temperature is speed or motion, volume is space, and moles is obviously the number of particles. So use these 4 ideas to help explain this. If pressure goes up, molecules collide more often. If temperature goes up, molecules are moving faster. Use those ideas to try and explain these, and then we'll get a chance to go through those together in class. All right, give it a shot. Good luck.